Okay, in this video I'm going to demonstrate how to carry out a one-way MANOVA involving an independent variable with two levels only. Basically with one-way MANOVA you have a single independent variable that is categorical. It can have two or more groups. Like I said, for this video we're going to be using just two groups, and then you'll also have a set of dependent variables, basically two or more, that are treated as continuous. And so we're going to do this demonstration using SPSS. So for this particular demonstration right here, we've got a single independent variable with two levels, as I said before. The independent variable is called plan, and it's coded 0 and 1. So essentially what we have is some fictional data that would be collected from a set of high school students concerning their plans or intentions after graduation. So the plan variable is reflecting intentions to attend college or not attend college. So the way it is laid out, a value of 0 reflects an intention not to attend college. A value of 1 reflects an intention to attend college. The remaining scale measures that you have right here are self-efficacy, perceived utility, intrinsic motivation, and present orientation. So we're going to see if students who intend or not intend to go to college differ in terms of their scores on these dependent variables. Just keep in mind that, in the context of MANOVA, it's a little bit different from the standard one-way ANOVA, where you are looking at group differences on a single dependent variable. In the context of a one-way MANOVA, you're still looking at group differences, but you're looking at group differences across a set of dependent variables that are going to be intercorrelated to a certain extent. So to carry out our analysis in SPSS, we are going to go to Analyze, go down to General Linear Model, and Multivariate. We'll move our independent variable over to the Fixed Factors box, and we'll move the remaining variables over to the Dependent box. Next, we'll click on Options and click on Overall and Plan, and move these over here so that we get the means displayed for our groups and overall. We're going to click on Descriptives, Effect Size. I often click on Power, even though it's not terribly helpful in many respects. And then Homogeneity Tests. So we'll click on that as well. Next, we'll click on Plots. If we want to get a profile plot for each of the dependent variables and looking at the mean difference in a plot, we can obtain that just by kind of moving plan over to the horizontal axis and click on Add. And next we'll click on Continue. Finally, we'll click OK, and we'll get our results. So first off, you'll notice that we have descriptive statistics associated with each of the dependent variables. So there's self-efficacy, utility, intrinsic motivation, and present orientation. We've got the means for each group, so the intention not to attend college group versus the intention to attend college group. You can see that self-efficacy is higher for the attend college group. Perceived utility is higher than in the attend college group versus not intending to go to college. For intrinsic motivation, it's higher for the attend college group, and then present orientation is a little bit higher in the do not intend to go to college group versus the intend to go to college group. So those are the basic descriptives. You also see that we have the standard deviations for the variables in each group, and also the sample sizes associated with each group. Now, down here you'll see that we have the multivariate test results, and here's our independent variable. And like I said, this is basically looking at a relationship between our independent variable, which is plan, and a set of dependent variables, which would be the self-efficacy variable, the utility variable, perceived utility, the intrinsic motivation variable, and the present orientation variable. So what we're doing is we're looking to see if, essentially, are there group differences across the set of our dependent variables. Down here are our multivariate test results, and most of the time we focus in on, or quite often we'll use Wilks lambda to test the overall effects. So we're going to use this row right here, and you can see right here that we have a Wilks lambda value. We've got an F value, the hypothesis degrees of freedom, the error degrees of freedom, p-value right here, and then we have partial eta squared, which we'll talk about shortly. Then there's that observed power I was telling you about. Really quickly, the only reason why I'm kind of downplaying this right here is because this is really just an estimate of the power of a test with essentially the same sample size as effect size, and it's essentially reflecting a likelihood of detecting a statistically significant result in future studies. So it's not terribly useful for this particular study. So at any rate, we'll also see over here we've got boxes tests, and this is pertaining to an assumption that is related to our multivariate test. So basically, boxes test is essentially the multivariate version of what we are trying to accomplish when we're testing equality of error variances using Levine's test in the context of a standard univariate ANOVA. So with boxes test, the assumption is equality of variance covariance matrices. So just really quickly, a variance covariance matrix, we have 4 variables. So essentially, along the principal diagonal, you would have the variances for each of those variables. And then on the off diagonal, you would have the covariances. So we've got the covariance between here, it would be variable 2 and 1, and it's the same elements are presented above the primary diagonal. So we would have 1 and 2 right here. The covariance between variable 3 and 1, and the covariance between 1 and 3 right here, and the covariance between 4 and 1, and the covariance between 1 and 4. So you can see we have a reproduction of the same values above the principal diagonal that we have below. We would also have the covariances between variables 2 and 3, 2 and 4, and then 3 and 4 as well. So the point is that we would have a variance covariance matrix for group 1 and 1 for group 2. And what we're doing with this particular hypothesis, our boxes test right here, is we're trying to test the equality of these variance covariance matrices. And if we have inequality of the variance covariance matrices, then that can call into question our results down here, because it can be the case where we would have an inflation in type 1 or type 2 error. So just really quickly, if basically, if our boxes test is indicating statistical significance at the 0.05 level or below, that's a conventional alpha level, then we would reject the null hypothesis and essentially be adopting the alternative hypothesis that these two matrices are unequal, in which case that would then bear on that question of the validity of our test results. So given that this right here is not indicating non-significance, then we are not going to assume that they're unequal, but we're going to assume that our variance covariance matrices are equal, in which case we can feel more security or trust or whatever in the interpretations of our test results. So that's why we care. Just as a quick aside, just keep in mind that this test is impacted as usual by sample size. So it can be the case that you can have a dramatic a large sample size and very little difference between the two matrices and end up rejecting the null. So sometimes it's worth your while to go back and look at other indices of or other approaches to evaluating this particular assumption. By the same token, it can be the case where if you have a low sample size, maybe you have an underpowered test and you fail to reject the null and conclude that the null is true, when in fact maybe it's better to assume that they are unequal. So that's one of the limitations of a test like this, but that's just that's something to think about as you move forward. So at this point, we're going to make the assumption that our equality of covariance matrices assumption is met, and we're going to look at the effect of plan on the set of dependent variables, and using Wilks lambda right here, and really in the context of a one-way ANOVA, or excuse me, one-way MANOVA with only two groups. All of our test results are going to be the same. So these are all the same values, but I'm really drawing your attention right here because you can have different test results when you have more than two groups. So there's Wilks, and you can see that we have statistical significance right here, and that would tell us that there's a significant multivariate mean difference between our two groups, the students who are intending to go to college versus those who are not intending to go to college. We have partial eta squared right here, where we can, in the absence of a good sound theory, in order to kind of make a statement about what constitutes large, medium, small, medium, or large effects, or previous research that would bear on that, we can utilize Cohen standards as sort of a rough guide for judging the magnitude of an effect. So keep in mind that Cohen standards really apply to the social and behavioral sciences. So if you're in a different type of area, maybe in physical sciences or something like that, where you have much less measurement error associated with your instruments, then these might be considered laughable. But in the social sciences, these are kind of conventions, which again really you ought to apply in those cases where you have really no leg to stand on when it comes to kind of judging what constitutes small, medium, and large effects. So just kind of using Cohen standards, we're going to use 0.01 for small, 0.06 for medium, and 0.14 would indicate a large effect. So you can see right here that the multi-effect would be considered large in our analysis. So next we're going to scroll down, and once we've actually, before we kind of get to that, once we've determined that there is a significant multivariate effect of the independent variable on the dependent variables, then we have to kind of follow up and try to isolate that effect and maybe even describe that effect. So there are various potential follow-up strategies that are available to you. So one follow-up strategy would be to carry out a series of univariate ANOVAs and essentially test for mean differences on each dependent variable. So you got right here plan, self-efficacy, utility, intrinsic motivation, and present orientation. And you can see that we have F-tests and our significance levels, effect size as well, for each of the dependent variables. So each of these are univariate ANOVAs comparing the two groups for each of the dependent variables. Now, the thing is that to keep in mind is that essentially this sort of violates the spirit behind doing the ANOVA in the first place. When you run the analysis of variance, or excuse me, when you're running the MANOVA in the first place, when you're running this, you're making the assumption that there are correlations among the dependent variables, and you're trying to kind of eliminate any redundancies when you're testing for group differences. So if you end up following up by using a standard univariate ANOVAs, you're essentially treating each of these dependent variables as if they are uncorrelated. So as a strategy, this doesn't make a whole lot of sense, except perhaps in those cases where you have very low correlations among these variables. Then it may make a little bit more sense, but then that also begs the question, why carry out the MANOVA? But at any rate, this is a conventional strategy, and you can see by default SPSS prints out the univariate ANOVAs. So we'll interpret that, and then we'll look at a couple of other options for following up the significant MANOVA result. So we have the relationship between plan and self-efficacy right here. You can see that there was no significant difference between the two groups on self-efficacy. We see that there was a significant difference between the two groups when it comes to perceived utility. With intrinsic motivation, there was a significant difference, and with present orientation, there was a significant difference. You can see that we had pretty much kind of a small effect for self-efficacy and considerably larger effects with respect to the utility, intrinsic motivation, and present orientation variables. So that's one follow-up that we can theoretically carry out to the MANOVA. Now, looking at the profile plots, because we asked for those, you can see that we have a plot for self-efficacy, the means not attending college versus attending college. You can see the mean is higher for the attend college group than the not attend college group. Perceived utility, the same general pattern. Intrinsic motivation, same general pattern. And then for present orientation, kind of the reverse pattern. So that pretty much takes care of the basic MANOVA results. So now let's look at another option as a follow-up. We've already determined that that we have a significant multivariate effect. One option as a follow-up is called discriminant analysis. And so discriminant analysis just basically is kind of a reverse MANOVA. So when we run the MANOVA, we have essentially our independent variable, and we're essentially trying to predict or account for variation in a set of dependent variables. So we have, dv1, dv2, and so forth. Now, in the context of discriminant analysis, we are essentially reversing things, and we're going to use the dependent variables from our previous MANOVA as predictors of group membership. So to do that, we're going to go to Analyze, go down to Classify, and then go to Discriminant. So we'll move our plan variable over to the grouping variable box, and under Define Range, we're going to put the minimum and maximum values. So we're going to put a 0 for the minimum, because that was the group coded 0, and 1 for the group that was coded 1. If we had 3 groups, let's say we had 3 groups and we had coded them 1, 2, and 3, then we would be using a 1 and a 3 right here instead of what we have in this case. So now we'll click on Continue, and we'll move our previous dependent variables over, and now they're treated as independent variables in this analysis. Under Statistics, we can ask for a lot of the same information we were getting before. We can ask for means, univariate ANOVAs, which is going to repeat what we had above, boxes M, which is the boxes test, and there is the assumption of homogeneity of variance covariance matrices in the context of discriminant analysis. Under Classify, we'll click on compute from, prior probabilities from group sizes, and click on Summary Table. And so there you go. So now we'll click on OK, and in this case, what's going to happen is that we are going to essentially form the information from our original set of dependent measures that we're now treating as independent variables. We are essentially relating these variables to our grouping variable. So this is essentially our plan variable, and these are our former dependent variables. So intrinsic motivation, self-efficacy, perceived utility, and present orientation. Now what's going to happen is that we're taking this information right here, and it is being combined into a new latent variable that's called a discriminant function. And it's that discriminant function that is related to group membership. So essentially what we're doing is we're looking at group differences on the discriminant function. And more than that, what we end up doing is, if this relationship is significant, then we go about the business of looking at the relationship between each of our measured variables and the discriminant function. So we'll look at structure coefficients and so forth in order to name the discriminant function. So then when it comes to talking about group differences, we won't be talking about group differences with respect to each of the individual variables. We can talk about group differences on the discriminant function. And now if it's the case that the discriminant function can't be named, we can still talk about the relative contributions of the measured variables to the group separation on the discriminant function. So let's take a look at our output, and I'll walk you through it here. So you can see we've got our group statistics, tests of equality of group means. All this is really just a replay of the same information that we had above in our tests of between subjects effects. And so within this table, it's going to look a little bit different down here because you can see that we have Wilks lambda value, but the F test and everything is the same. Box's test down here is providing the same results that we had before, and then when we move down below, you can see that we have a summary of canonical discriminant functions. And in this particular case, this is essentially looking at the relationship between the discriminant function that is formed as a composite of the information of our original variables, its relationship to the planned variable. So what we have right here is what's called a canonical correlation, and it's going to range between 0 and 1, and it's pretty much interpreted like multiple R in the context of regression analysis. So it's the correlation between the discriminant function and our grouping variable. And then down here we have a significance test, which is essentially a test of the significance related to the canonical correlation. Now, I'm just going to give you a forewarning that in the future, if you're running a discriminant analysis that involves more than two groups, then you can have more than a single discriminant function. So you can have a function 1, a function 2, and so forth. And so then there would be tests related to the multiple functions. But in this particular case right here, we only have one discriminant function that we're talking about, and so we can see that the correlation is 0.807. So that's a pretty large relationship between our discriminant function and our grouping variable, the planned variable, and we would say that it's statistically significant. So if our discriminant function is statistically significant, then we can go about the business of either naming the function or just trying to talk about which of the original measured variables are most related to that function. I do want to point out that essentially this was kind of a given already, because you'll see the Wilks lambda value right here is 0.349, and you'll notice that if we go up here into our table from the multivariate test, we have the same Wilks lambda value. So essentially the test is nothing more than the multivariate test that we had before. So when we are looking at the multivariate test, you could also think about it as testing for group differences on the underlying discriminant functions. So you can think about it that way. So now that we've determined that there is a significant relationship between our discriminant function and the grouping variables, we can name it and describe it. So we can use the structure matrix to help us name the discriminant function. And so these are just correlations, Pearson's correlations, between each of the measured variables and the discriminant function. So you can see that perceived utility is correlating 0.863, it's very high. Intrinsic motivation is correlating high. Present orientation is actually correlated negatively, fairly highly with function 1. And then self-efficacy is really minimally related. So you can see that I could use these, these three variables right here to name the function. So I could name it something like future approach motivation or something like that. So I'll just call it future approach motivation to give it some kind of meaning. And so then I can say that the two groups are differently different in terms of their level of future approach motivation. So I can do that. Another option, if I can't name the discriminant function, then what I could do is I could just say, well, which of the dependent variables is that was in our MANOVA, which of them were really contributing to group separation on the discriminant function. So these are standardized canonical discriminant function coefficients, and these are analogous to beta weights in the context of a regression analysis. And so so we could say that perceived utility is highly related to the function. Intrinsic motivation has a lower relationship, and present orientation is exhibiting a negative relationship, but it's fairly high. So if we take the absolute values of these, we can sort of rank order these variables in terms of their relative contribution. So you can see utility is contributing most to group separation on the function, followed by present orientation, followed by the intrinsic motivation, and then the weakest contributor to group separation was self-efficacy. So that's essentially the name of the game. And then if you look down here, if we want to if we go back and we look at our the discriminant function in terms of what we named it, and really the structure matrix is your best bet in terms of naming any of the discriminant functions. It's pretty much like interpreting a structure matrix in the context of factor analysis or principal components analysis. So we can also look at functions at group centroids, and so you can think about it as there's one underlying discriminant function, and we're going to call this, again, present, or excuse me, future approach motivation or something like that. I'll just call it FAM. So at 0, there would be no group difference, and then in this particular case right here, the do not attend college group, it would be plotted on this side here, and the attend college group would be over here. So you can see that the mean of the discriminant function was higher for the attend college group than the do not attend college group. So you can see that and that's kind of what you would expect if you have this sort of greater levels of future approach motivation for the attend college group. So that's a demonstration related to our discriminant analysis as a potential follow-up to MANOVA. There's another option which is called step-down analysis, which I don't really see very often in the literature, but it is something that you could theoretically do. But this does involve utilizing some syntax. So right here, what I've done is I just created a little syntax file, and I'll link this up on my video description so that you can download this. But you'll see that we have a statement. It says MANOVA, and then followed by the names of my dependent variables. Actually, this is a former run. I'm going to also add in, I'll add in present here as well. And in this particular case, step-down analysis is basically a series of analyses where at each step along the way you're adding in covariates. So if I have 4 dependent variables and I'm looking at group differences on them, the first analysis will start, the first variable that's being compared at is this variable right here. So this is going to be included as the dependent variable in the first analysis. So self-efficacy will be included as a dependent variable in a standard one-way ANOVA. Okay, so then at step 2, perceived utility, that will be added in as a dependent variable, but in this case it will be an ANCOVA, where essentially during step 2 you are controlling for the step 1 dependent variable, which is self-efficacy. So that would be step 2. Step 3 in this case would be intrinsic motivation, and that would be an ANCOVA. And we would be looking at group differences on intrinsic motivation, controlling for both self-efficacy and perceived utility. And then at step 4, no surprises, it's going to be present orientation. It would be an ANCOVA, controlling for the previous 3 dependent variables. So you're essentially kind of stepping through a process where you essentially are assigning a certain ranks or a sequence in which dependent variables are added, and at each subsequent step you're controlling for the previous dependent variable from the previous step. So another example too, let's say that I want to reorder. Let's say I want to use present first, followed by intrinsic motivation, perceived utility, and self-efficacy. I can do that, in which case present would be in a standard one-way ANOVA, followed by intrinsic motivation, which would be an ANCOVA, controlling for present, utility, and then self-efficacy. So let's take a look at both of these approaches so you can see them. And you'll also see it says by, and then I have plan, which is the independent variable, and I've got the minimum and maximum value for the plan variable. And actually it should read 0 and 1 because those were the codes. So this was actually from a previous run that I had done with a different coding system. So in this case, you have to use the actual codes associated with your groups. So let's run the analysis. I'm going to highlight this, click on the green button, and so here you go. So you can see that we have a lot of, we have our descriptive statistics for each of our variables. It's not as nice looking as when you run the standard MANOVA, but you'll see down here you've got your multivariate tests of significance. There's our wilts that we had seen before, and our multivariate test results right here. When we scroll down a little bit further, you'll see too, these are the univariate Anova follow-up tests that were in the previous table for tests of between subjects effects. So, if I scroll up here, I can just show you that is the same information that is contained in this table right here. Then, the step-down analyses are presented below, and so now you can see that we have, it says variable, and so these are the dependent variables that are added in each step. So step 1 was self-efficacy, step 2 was utility, step 3 intrinsic motivation, step 4 was present orientation. So the test of differences between the two groups on self-efficacy, that was not statistically significant at the 0.05 level. When we run the ANCOVA with utility as a dependent variable and self-efficacy as a covariate in the model, we see that there is a significant difference between the groups on perceived utility after controlling for self-efficacy. At step 3, when we add intrinsic motivation as the dependent variable and control for these other two variables, we see that there's a significant difference on intrinsic motivation. And then at step 4, present orientation, we see that there's a significant difference after controlling for all three of these variables. If we want to run it using the other approach, we can certainly do that. We'll try it this way and see what happens. And so in this case, all of our MANOVA descriptive information, MANOVA results are going to be the same. The only difference is now the step-down test. You can see we have present, stepped at 1, intrinsic motivation, perceived utility, and self-efficacy right here. So you can see that the difference between groups on present orientation was significant. Difference between groups on intrinsic motivation after controlling for present orientation, that was significant. The difference between groups on perceived utility, controlling for the previous two DVs, is significant, but then self-efficacy is not statistically significant. So this is an option as a follow-up test. Just keep in mind that it's a little ambiguous about what ordering you should enter your dependent variables in to perform the step-down procedure. So usually you would want to let some theory or some rationale be your guide in terms of which variables are entered at each step. And so you almost have to think about it along the lines of what you would do in the context of a hierarchical multiple regression, where you sort of have some theoretical or logical base for entering your variables as predictors in a sequence of steps. Now, if you didn't want to do this, one final option is just to run a series of ANCOVAs where you look at the difference between the groups on each dependent variable while controlling for all of the other variables that were the DVs in your MANOVA. So you could certainly do that as well, and you would not be violating the spirit of the MANOVA. So in this particular case, instead of so what you could do is you could just run go to Univariate, stick plan in the fixed factors box. We'll start with self-efficacy and then control for everything else. And actually by doing this, I'm essentially going to end up with the same results as this step right here, because you can see for this analysis it involved controlling for all the other DVs. That's from the step-down analysis. So, but just in the spirit of doing this, we'll just click on options and click on our usual information that we are going to request. and I'll click on OK. And so you can see right here that there's our plan variable in relation to self-efficacy, controlling for these three covariates right here. You can see there's the p-value of 0.782, minimal effect size, negligible, and so it was not statistically significant. So like I said, there's our F value that we had just observed when we ran the step-down analysis. Next, we'll go through and we'll run our analysis with take self-efficacy out. We'll put present orientation in, and we can run that. And so now you can see when we are controlling for all the other variables, we have plan, and you can see that we have significant relationship between plan and present orientation controlling for these other variables right here. And so you can just do that with each of the variables treated as DVs, with the others treated as covariates in the model. So there's IM right here. We'll put that in. And so you can see right here we have close, near significance at the 0.05 level for plan and intrinsic motivation. And then when we have utility, you can see that we have significance there. Just keep in mind that obviously as we're going through these multiple tests, you do have that risk of increasing type 1 error rate across a set of tests. So you can see that we've conducted a number of tests using the Anova approach, but then also the same would really apply in the context of the step-down approach, or up here where you're looking at group differences using the Univariate follow-up approach. So we do have those kinds of issues that you need to pay attention to. Obviously, the discriminant analysis, we only had essentially one test, which was a test of the relationship between the discriminant function and the grouping variable, and then we went about naming the function. So obviously there are lots of different approaches that you could theoretically adopt, and so I just wanted to bring you up to speed on those on some of these options in the context of two-group MANOVA. So that will conclude this discussion, and I hope you found this video useful.